Brewer, Thoemmes, and Rosenthal published a paper on an idea of continuously cumulating meta-analysis in 2014. Now, continuously cumulating meta-analysis, or CCMA, is the idea of using meta-analysis in a continuous manner. So rather than waiting for a number of studies to be available and then carry the meta-analysis, is to do meta-analysis progressively as each study becomes available. And actually this idea has all the potential of being very good for the advancement of science, especially in psychology and related disciplines, by accumulating evidence. Unfortunately, Brewer and collaborators use NHST, or null hypothesis significance testing, to make their argument, and in my opinion this turned out to be a big fail. Now, the argument is the following. The probability of replication depends on research power. Therefore, if you join low research power plus small sample sizes, the low small numbers just kicks in there, then what you get is a low probability of replication when using conventional significance level. And the logic of CCMA, actually, what it does is try to resolve this by accumulating previous studies. So estimates are more accurate and the total sample size gets larger. Of course, with a larger sample size, then you get greater research power and also greater probability of replication. So it seems that CCMA is a win-win solution, except that they use NHST to make their arguments, and we know that NHST is an incoherent mishmash of two theories, that of Fisher and Neyman-Pearson. So philosophically speaking, is an irrational argument, and therefore leads to pseudoscience. Now, let's put this idea of NHST as pseudoscience in perspective. Okay, so imagine the following scenario: that there is a theory there that says the symbol of a cross is used for the summation of two numbers. Therefore, 10 plus 2 equals 12. And there is a second theory that says that the symbol of a slash is used for the division of two numbers. Therefore, the same numbers, 10 divided by 2 equals 5. So it results in a different solution, right? Now, there is a new symbol in town. Okay, there is a horizontal line through a column, which a minority of people are using as a division symbol, as a slash, right? Now, of course, there comes a logical man who fancies the new symbol, but doesn't know much about its use as a division. And indeed, he makes the following deduction. Well, the symbol actually resembles the summation symbol more than it resembles the division symbol. Therefore, it stands to reason that it is, or it must be, a summation symbol. Therefore, for him, or he says that 10 with the new symbol, 10 and 2 used or conjoined by this symbol equals 12, because it's a summation, and therefore this actually is a logical deduction, rather than 10 divided by 2 equals 5. So, although his deduction is logical, based on this resemblance between symbols, it is actually irrational, because we know that it doesn't mean that, right? So Brewer et al.'s argument actually is the theoretical equivalent of saying that a slash and a summation are the same, because the symbol, this new symbol, is alike to the summation symbol. Now, the slash is equivalent to Neyman-Pearson theory of data testing. The summation is the Fisher's theory of data testing, and the new symbol, the horizontal line through the column, is NHST, a mix-up of those two theories. Okay. And indeed, when you look at Brewer's article, you can see this in context. I use orange to highlight relevant text under Fisher's theory, and I use blue and green to highlight text that is relevant under Neyman-Pearson theory. And as we can observe, both theories are together in the same argument, and actually together in a mixed way. But look at the chunkiness of the information. It's like mixing oil and water. You can put them together, but they don't mix that well. So actually it seems that even when the articles try to create this emulsification by putting the two theories together, they don't actually mix that well, and the argument could have been done for each of the theories individually. And this is what I want to do in this presentation, to look at those two theories independently and to check the implications of Previous et al.'s article on those. So let's start with Neyman-Pearson's theory. Now, Neyman-Pearson is a fixed approach to data testing, precisely for with the purpose of controlling power. So there is a fixed effect size, alpha, beta, and fixed sample size. And it also assumes repeated sampling from the same population for replication purposes. Okay, so under this approach is actually incoherent to pull data from different projects, because doing so changes above fixed parameters. Right? If you cannot control those parameters, then you can use this approach. Therefore, under Neyman-Pearson's, replication reduces to account of the number of successful replications in the long run using those fixed parameters. And this is exactly what Prever's Table 1 shows. This is a repeated sampling context. They use 10,000 replications using the same fixed parameters. Now look at the blue part. The highlighted blue text is information for single studies. Okay, in case 1, for example, for each study having 50 sample size of 50. So the expected power was 41%, and actually the obtained power was about 41% as well. So it's coherent and with expectations under Neyman-Pearson approach. Now, as I said, under this approach you cannot combine studies for a meta-analysis, because actually you already know the parameters, right? But we can use this, and this is the green highlighted text, in order to see the expectations when sample sizes are larger. In this case, when sample sizes are 100. In this case, the expected power is 70%, and the obtained power is also 70%, or about 70%. So this table and the whole simulation process done by Brewer actually does not prove that CCMA improves replicability, but that power improves replicability. In this case, I mean power in the context of known population parameters and repeated sampling from the same population, which is exactly what is expected under Neyman-Pearson's approach. Alright, let's look at Fisher's approach now. What Brewer et al. Could have said under this approach. Now, Fisher's theory is more ad hoc than Neyman-Pearson. Uses for exploring research when much of the information is unknown. So Fisher doesn't have interest in power, or actually cannot actually control it in advance. Has no interest on effect sizes, has no interest on controlling type 1 and type 2 errors, and therefore is also unable to estimate sample size for significance in advance of the study. It is also an evidential approach, and it has little use for replication in the long run, including next study statistical replication. So actually Fishers would prefer the accumulation of evidence, for example from previous studies, in order to learn more from the research. Okay, so this is actually what CCMA and meta-analysis provides. This is the whole argument of meta-analysis and therefore of CCMA. What is also important here is that under these conditions is incoherent to replicate the studies in the way Brewer did, I mean under the banner of power, when power is not relevant to Fisher's approach. So that also leads us to say that replication per se, understood as you know, the simulation that Brewer carried out, is also irrelevant. Just counting the number of successful replications or the percentage or probability of replication is irrelevant, because it doesn't suit this approach of Fisher's approach. But on the other hand, we know that CCMA is appropriate, and it is appropriate because it makes estimates more accurate and increases statistical sensitiveness, which is similar to power but is not power. Alright? And this is actually what table 2 shows. So here we have two examples of studies, two studies with the small sample size of 50, right? So the original study was carried out, you get your probability, your p-value of 0.03, whatever, and you then can estimate what the effect size in the population may be. And in this case, that first study returns a coherence d of 0.52. We know from the simulation, because it's an artificial population that we created, that the actual effect size, the difference between the groups in the population, is 0.50, right? So the original study actually here shows that there has been an overestimation of the effect size, but we don't know it, because we don't actually know what that the population effect size is. So this is like, in hindsight, we know it's an overestimation. So a second study, a replication attempt, will be carried out, same sample size, etc., and also may return a different result. In this case, the p-value is not significant, you know, using conventional significance levels, and the estimation of the effect size is below what we know in hindsight the real effect size in the population is, so it's 0.37. So of course, doing studies like this, you can see the p-value dancing around, you can see the estimation of the effect sizes dancing around, but, and this is where CCMA comes handy, when you accumulate those results, then the estimates becomes more accurate. It's 0.49, pretty much very close to 0.50, which we know is the correct effect size in the population. And incidentally, the p-values, because also the larger sample size, reduces to 0.16. And here is where CCMA provides value to research. CCMA helps obtain a more precise estimate of the population parameters that are unknown to us, and of course it provides a more precise estimate than individual studies can do. And also CCMA increases sensitiveness by increasing sample size, and may lower the p-values as well. Now, sensitiveness is related to power, but it's not equally definable as power, nor equally controllable, as we have introduced earlier. So, what's the main point to make here? Well, the main point to advance is that Brewer et al.'s argument could have been better if they had taught NHST. Had they done that, they would have realized that CCMA is not needed for increasing power and the Neyman-Pearson's approach, because for increasing power, what you need is that increasing power. You don't need CCMA. Instead, CCMA is the optimal fuel for propelling Fisher's approach, which is incidentally the most commonly used in research. It's also the optimal fuel for increasing estimation accuracy, and is the optimal fuel for increasing research reliability, which in some way is linked to replicability, but again is not the same replicability defined as under Neyman-Pearson's approach and in the simulation they use. And pretty much this is what I have to say. There's more readings here if you wish to read further. And the main point, ditch NHST from any arguments, and that will be the best solution.